Hey guys, welcome back. So we're going to be doing the lab lecture for experiment 8. Now, experiment 8 is not very complicated in terms of the data collection, but there is some work that needs to be done with the data processing. So let's take a look at what we've got here. Go ahead, share that out of the way. So this is the experiment that we're looking at that was done in the laboratory. Okay, so we take a zinc cell and we set that up with copper, and we connect those two to look at what is the voltage that exists between those two cells. So we have zinc as our oxidation, Zn solid going to Zn2 plus 2 electrons, and our reduction is copper, Cu2 plus 2 electrons going to Cu solid. Okay. When we do this, the way that this is typically done is to have two different cells that are connected by a salt bridge. What's the purpose of the salt bridge? The purpose of the salt bridge is to make sure that we have electrical neutrality. So as we continue to move electrons from one cell to the other, we need to move negative ions into that same cell to maintain electrical neutrality. Okay, so that's what we're talking about for that. Now, while that's normal, that is not what we do in our laboratory. And the reason that we do that is because we don't want to have a salt bridge that can be forgotten. So we use something else. It's called a porous pot system. And this was actually the way that this particular cell was originally designed. So this is a historical thing. What you'll see here is a diagram of that setup. So there's a beaker that contains copper sulfate. That's a solution down here. Okay. Inside, there is a porous pot. That pot allows ions to travel between the two solutions. That porous pot contains zinc sulfate. There's a zinc electrode right here, and there's a copper electrode right here. Notice that they are not touching each other. They are both connected to wires that go into this LabQuest voltmeter. So the voltmeter reads the voltage between those two electrodes. Okay. You'll see that there is a standard cell that we do and a non-standard. We'll talk about the details of that in a few seconds. But there's data here in the data file that you'll find on D2L that indicates what the voltages were at time 0 and time 5 minutes, and then observations for both of these particular cells. Now, let's talk about this. So when we do a standard reduction potential, that's based on 1 molar concentrations of our solutions. That's not always the case. So what happens if we're not in a situation where we have a 1 molar standard? Okay, we can still use the standard cell voltage and do a correction based on the fact that we're not at the 1 molar concentrations we would expect. So we calculate our standard reduction potential using this equation right here. E cell equals E naught oxidation plus E naught reduction. And of course, what we need to do when we do that is figure out what the E naught for both of these things is. Now, give me 2 seconds because So one of these has a value, and I'm looking at my exam handouts, the standard reduction potential table. So my Zn solid going to Zn2 plus is an oxidation, so it's 0.76 volts as an oxidation. So when it's written as a reduction, it has the opposite sign. Okay, so don't forget that that's what happens with that. There we go. So that's for this one right here. Okay. Now, when we look at the other one, the copper one, let's go ahead and do another insert over here. And our copper one, and I find that Cu2 plus 2 electrons goes to copper solid, is 0.34 volts. Okay. So that is the voltage for that particular cell. And hopefully I can make that a little bit bigger so that we can all see that. Okay, and so those are the two cells for those two half reactions. Now, it says down here in equation 15 that E cell equals the E naught for the oxidation plus the E naught for the reduction. When it says E naught oxidation, that means we've taken the reduction potential for the one that's the oxidized species and flipped the sign on. Because when we reverse the reaction, we flip the sign. So that means that we'll take our E naught cell for that. So our E naught cell is equal to that E naught for the oxidation plus the E naught reduction, and that's equal to the 0.76 volts plus the 0.34 volts, and that's 1.10 volts. Now, when we talk about this in lecture, one of the things that we said was the E naught cell equals E naught reduction cathode minus the E naught reduction anode. What that means is that when we use those values, they need to be the values as they exist in the table. We take the value for the cathode, okay? The cathode is the one where the reduction occurs. So that would be the 0.34 volts. It's a red cat. Remember, reduction occurs at the cathode. And then we subtract the one that occurs at the anode. Lose electrons, oxidize, LEO occurs at the anode. Okay, both vowels, so they both occur. So that occurs there. And then we subtract the negative 0.76 volts that we would read from the table. Okay, so that's the value as it exists in the table. That gives us the exact same number. Absolutely it does. So either way you choose to handle it is perfectly fine. You will need to recognize which of those equations is correct. There is a question about that on one or more of the tests. So that's how we find our standard reduction potential. So that's our E naught cell. And that naught means that we're at 1 molar concentrations or 1 atmosphere for gases. So those are our standard conditions. Okay. When we're under non-standard conditions, and things are not all 1 molar, then we have to use this equation right here. And that's equation 16. And it's listed as the Nernst equation. Now the Nernst equation says E cell is equal to E naught cell minus RT over NF ln of Q. Okay. Now, if we make a change so that we don't have to work with the natural log, we don't want to work with R and F because they're constant, so we can include those, and we assume that our temperature is room temperature every time, then we can get equation 17, okay, which is E cell equals E naught cell minus 0.0592 over N log of Q. Okay. So my E cell for my non-standard conditions is going to be the E naught cell that I calculated here. So the standard conditions minus the 0.0592 over N, which is the number of electrons that are transferred, times the log of Q. Now N for this, for both of these processes, are 2, right? Because we have, which direction? Sorry, I didn't write it down. I hate it when I do that. So it's Zn solid going to Zn 2 plus 2e minus, and then Cu 2 plus 2e minus going to Cu solid. Both of those are 2 electron processes, so we know that that N is going to be equal to 2. Now, Q, log of Q. What was Q again? I have a vague recollection of what Q is. Q is related to the equilibrium constant, but it's the situation that exists when we're not necessarily at equilibrium, right? So Q can exist at any time, and Q is equal to the concentration of the products over the concentration of reactants raised to their stoichiometric coefficients. Okay. So I need to look at what are my products. Well, all right, my overall reaction for this is a Zn solid plus a Cu2 plus, because we cancel those electrons, going to give me a Zn2 plus Cu solid. Okay, so that's my overall reaction. That means that Zn2 plus is my product. And of course, that's a 1, so I don't have to raise that to a power. And my reactant is the Cu2 plus. So that's my Q expression. All right, we'll need that when we get to the calculations for our non-standard conditions. So we do this in 2 ways. We do one with standard solutions, and everything is hunky-dory, and we should read the data that comes from that, which we have. That has been given to us. I'm not showing it to you right now, but we have it. Oh, I'm sorry, excuse me. I swear this happens every time I get on camera. And then we do it for our non-standard conditions. Now, understand that that porous pot is a salt bridge. That's what it is. It allows those ions to transfer so that we maintain electrical neutrality. And this is useful in the laboratory because we don't have to remember to put this salt bridge in to make it work. It will work as long as we put the porous pot into the other beaker. Okay, so that's one of the reasons that we use it, because it's less problematic to get it to work. Okay, so we do our standard, we connect all of our stuff. Where's my, so we connect the clamps to both of these, connect them to my voltmeter, and that gives me 1.090 volts at time 0. And after 5 minutes, it's 1.10 volts. Okay. Now, over time, both metal electrodes change color as the reaction proceeds. Okay, I see the zinc turning dark, and I see the copper getting really shiny. All right, that's what happens. When we look at our non-standard conditions, let's go talk about what that means. So down here, we see the effective concentration on the potential of a galvanic cell will now be studied. And we're going to repeat what we just did. We're just going to change some information. It says prepare a dilute copper sulfate solution by adding 2 milliliters of 1 molar copper 2 sulfate to 98 milliliters of water. Okay, so when I do that, I add 2 milliliters of 1 molar B1, M1, M2, E2. This is to the X that I'm solving for is at M2. And my V2 is the total volume, which is 100 milliliters. And you can't see that. Why are you not responding to me? Sorry, my mirroring is not working. So give me a second. Let me close that out and try this again, because it should be showing you that. There we go. So remember that our total volume is that 100 milliliters. So we take the 2 milliliters, we add the 98, the total volume is 100. We need to put that total volume in for volume 2. So that gives me that calculation there. And so my X value is going to be 2 milliliters over 100 milliliters times 1 molar. And that will give you the new concentration. Okay. And then we set up the exact same scenario. But when we do that, we need to use this right here. And so our Q is going to be based on the new copper sulfate concentration. So the Zn stays the same. Our Zn is still 1 molar, but our Cu2 plus is this calculation right here. And so that will help you determine what your non-standard voltage should be. That's our theoretical value for our non-standard voltage. This is our theoretical value for the standard voltage. Okay, so we should have a theoretical for both of them and then an actual that we measure in the laboratory. Okay, so this is the one that we're going to measure in the laboratory, and that's the data that you have. Again, you should find this on D2L in, let me see where I put it. Let me bring that up so I can show you. So we go into D2L. Someday it will respond. I go into your shell. I go into content. This is exam 2. This is a voltaic cell, which is in here. The galvanic cells experiment 8. And you will find that experiment 8 data is right there. Okay. I'm going to move this up a little bit because I want it up here. Oh. Okay, never mind. Well, I think I have 2 of them now. Awesome. So this is the one I want you to use. This is the one that I've been showing you. Okay, and this video will appear right here when we're ready for that. Okay, so that's where you'll find that. Now, your summary has more than just this data. Okay, so let's talk about what else is in this summary. Assuming it ever decides to listen to me. So we want to look at where is our objective. And the objective for this lab is on page 50. Remember to put it in your own words. The balanced redox reaction, I wrote it previously, but it's on page 50 as well. Theoretical standard potential, E0 for the ZNCU cell, is this thing right here. It's not going to fit there, but okay, fine. And I'm actually just going to copy, say, refer back. Undo. There we go. Because I wrote that out for you, so you should be able to look at that. Now, calculate the molarity of the copper 2 sulfate. That's at M1V1 equals M2V2 that we did on the previous page. And I'll let you calculate. And then our non-standard potential is the one that I set up for you on the last page. Okay. Now, diagram the galvanic cell that you set up in the lab. Now, I have provided you with this image. Under no circumstances is it okay for you to copy and paste this image into this document. It is entirely appropriate that you either make your own image or hand draw that. Either one is fine, I don't care, but you can't steal my work, okay? So don't do that, because if you do, I'm going to know, and it's going to irritate the heck out of me. That is plagiarism, and that is not a good idea, because that is something that I can have you written up for. All right, so that's what you're going to do there, is that diagram that you're, so replicate. And we do this because we want you to understand that what we did was a non-standard setup. The porous pot works just fine, but you need to understand that we aren't always going to see it as 2 cells the way that's often presented. Okay, so that's not always the case that we're going to see. Discussion and reflection. Discuss any differences between the theoretical voltages and what you observe. So if there are differences between what you calculate and what you observe, which there may be, talk about why. Why might that happen? So give me some thought as to why that might occur. Okay? Specific things that I know can occur when the data is collected. If those electrodes are too close to each other and they touch, we can have electrons transferred directly between them without going through the voltmeter. So we don't measure them, but they get transferred. Okay, that's one thing. Improper dilutions of the solution. So if it's not made correctly, then that will affect the data that you're looking at. If the original solutions were not made correctly, if it's not actually 1 molar and we have issues with that, then that may cause problems that we have there. Contamination of those solutions can cause problems as well. Okay. So those are things that you can see in what we're looking at. One other thing that I will tell you is that you are instructed to take these electrodes and scrub them with steel wool. And if you don't do that, it can affect the data that you see. And that's because we have formed a layer on the surface of the metal that we need to get rid of when we do this experiment. So another thing is not cleaning out the porous pots correctly, so not making sure that they're rinsed of all the salts that are in them. That will affect the data that you're looking at as well. Okay. And number 6 says, discuss the effect on the voltage of the cell from diluting the copper if sulfur solution in terms of Le Chatelier's principle. So I want you to take this balanced equation, which if I'm not mistaken, Zn solid plus Cu2 plus Zn2 plus Cu solid. So if we change this concentration, so that concentration right there is lowered because we diluted it, so it is lowered. What effect should that have on this particular reaction? Explain that to me in terms of Le Chatelier's principle. So is it going to go forward or is it going to go backward to deal with that? Right? Which direction is it going to go? And what do you think that effect is going to have on the voltage that you see? So if it goes forward, would that voltage go up or down? So that's what I want you to think about there. That's what that question is designed to ask. So I'm looking for two things. Did you predict the direction that it would move correctly? And two, what effect would that have on the voltage? Right. So that's our summary and discussion. Cool, that was fun. Let's close that out and let's talk about the post lab. Post lab. Write the shorthand notation for the zinc copper galvanic cell that you constructed. Shorthand notation means the cell notation. So remember, if we're talking about this being the Zn solid plus the Cu2 plus going to Cu solid plus Zn2 plus, then my cell notation for my one that's on the left is going to be, and lose electrons oxidize is the one that we put on the left by convention. So my Zn solid should be phase boundary with Zn2 plus. Initially, this is 1 molar. And there's a new cell. That porous pot is a new cell. And then we have our Cu2 plus, which there is 1 molar. And then Cu solid. Okay. So this is your standard one. You also have to write one for the non-standard. And I will let you do that because you need to have that concentration that you put in for the non-standard cells. So you get to do that one. Next one says, if the concentration of both solutions were changed to be 0.1 molar instead of 1 molar, would the theoretical voltage have changed? So use the Nernst equation. So you're being asked to use this for this process, which is a 2-electron process, log of Q. And you want to know what's the effect if we change them both to 0.1. So you get to plug them both into your Q and see what happens. All right. If the concentration of the zinc sulfate solution were changed to be 0.1 instead of 1, and the copper remained 1, would the theoretical voltage have increased, decreased, or stay the same? And you can look at Le Chatelier's principle. I actually calculated the difference and then looked at my equation to say, okay, I changed the zinc sulfate, so I changed this one, it went down. What effect did that have on my reaction? Which direction did it go to compensate for that? And that's why that voltage changed the way that it did. Okay, so that's the one that we talk about there. And so I use that again in both places. Now the next one says, use the standard reduction potential table to decide if a reaction would occur between each of the following combinations if used in a galvanic cell. So Al and Al3 plus. So I see Al3 plus 3E minus goes to Al, and this is on the handout, and that's negative 1.66 volts. I see Ca2 plus, and actually it says Al to Al3 plus, which means that we're looking at the reverse of this. So rather than looking at it as the reduction, we want this to be the oxidation, right? And hopefully you understand why I say that. It's because we're going from Al to Al3 plus in the way that's written. Okay. So rather than it being this reaction, we want to look at the oxidation, which is the exact reverse. and AL3 plus 3E minus, and that voltage was 1.66 volts because I reversed the direction on that. So that's the value that I get there. The Ca2 plus has to be in this table somewhere. Apparently isn't in my table. So I would have to go and find a table that contains that value. Give me 2 seconds and I can find a table that has that value. So Ca2 plus 2 electrons is negative 2.76. So Ca2 plus goes to Ca solid plus, and I need my electrons on the other side, 2E minus plus. And that's negative 2.76 volts. So can I combine that to make a spontaneous cell? Remember that spontaneous my E naught is greater than 0. Okay, so you need to figure out, can you do that with the values that you've been presented? Okay. If I look, and I'm just going to keep this over here in case I have to look anything else up, Fe3 plus to Fe. Now here's a tricky one. So when we talk about Fe3 plus to Fe, the value that's in my table, I have Fe3 plus an electron going to Fe2 plus. But I also see, if I look, no, actually I don't see it there. So usually what we'll find is that we have Fe 3 plus going to Fe2 plus and then Fe2 plus. Fe3 plus to Fe2 plus 0.77. And then it says Fe2 plus goes to Fe, and that one is listed as negative 0.44 volts. And so if I want to talk about Fe3 plus 3 electrons going to Fe, I need to add those two together. And so that's the value that you would need for that particular reaction. Your Zn to Zn2 plus is on the table. That's the negative, well, Zn to Zn2 plus is positive, positive. Again, because that's the oxidation, so that's the positive. H plus to H2 is always 0. That's our standard that we measure against. So H plus to H0 is always 0. Okay. And Ag to Ag plus, we're going to be talking about the oxidation of Ag. Ag to Ag plus, I see right here. But we want the oxidation of that. So since this reduction is written as 0.8, that oxidation is negative 0.80. Okay, and that's for my standard reduction potential table that's in the exam handouts. Fe2 plus, we have that one is written down there. It's the Fe2 plus. That's a negative 0.44. And the Na is in my, it should be in my table. There it is. So the Na to Na plus is going to be positive 2.71. And 2 plus to Fe, yep. negative 0.44. Okay. So we need to calculate what is the E naught cell for those 4 reactions. For 2 of them, it should be positive. For the other 2, it should not be. For the one that's positive between A and B, calculate the standard voltage for the one reaction. So what is the E naught for the one that does happen? Okay. And consider C and D, you want to calculate that voltage. Excuse me, I'm sorry. I'm so sorry. And then in number 5, briefly explain the purpose of the salt bridge. So why is that salt bridge there again? And I keep saying it, and hopefully you keep hearing it. The presence of the salt bridge is necessary to maintain electric neutrality. If we don't have it, the electrons can't move because we will end up with charged species that we cannot have. Okay? So that's the purpose of the salt bridge. And that is everything for our post. So hopefully that takes you through everything that you need. Again, if you need to look up those values, not all of them are present here. I don't care where you get them from. I really don't. All tables should be the same. Should be the same. So go and find them, find the numbers that you need, and then calculate what you need to calculate. That should take care of everything for experiment 8. Now there's going to be one more detailed walkthrough for experiment 9. I will do that over the weekend. That's the last lab where we're going to collect data. For experiments 10 and 11, you will be doing ALEX only, but I will talk some about what you may see on the lab final because of those experiments. Okay, so I hope that's everything we need to talk about today. I'm going to go ahead and stop this and get this recorded so that you guys can watch it, and I will see you again soon. Thanks, guys.